Hello, everyone. Welcome to Scala chip design from zero to hero. My name is Oron. I'm the co-founder and CEO of DFiant. It's a company that does design services for DevOps and FPGA design. And if you don't know what FPGA design is, then good that you come to this talk. So the outline for this talk is we have an introduction for hardware design, what it is, and how to use a library that we developed called DFHDL for hardware design, plus a live demo, a real live hardware demo right here. And we'll also cover the magic of Scala 3 in making DFiant HDL. And we have a surprise quiz, and you get a prize. You potentially get this hardware development kit, not the phone. And hopefully have potential for some questions. So when we get into hardware design, I look at this meme and I think people complain about Scala tooling and Scala compile times, and basically you know nothing. Like Jon Snow, the real problem is in hardware, and hopefully what we aim to do is simplify that using Scala. The late Alan Kay says, people who are really serious about software should make their own hardware. That's why you should really care about hardware. But to think of it, hardware is done with software. So this concept can be expanded to people who are really serious about hardware should make their own software to make their own hardware. And this is the concept of CAD, computer-aided design, or EDA tools, electronic design automation, is to make the tools that enable you to be productive in making hardware design. So again, I'm saying hardware design again and again, but within the context of this discussion, what is hardware design? Let's get our bearings. But I'm not talking about real bearings or mechanical design. I'm not talking about cogs and things like that, not mechanical design. I'm talking about electronic design. And within electronic design, I'm not talking about board design. I'm talking about component design. But with components, I'm not talking about discrete components, diodes, or resistors. I'm talking about chip design. But within chip design, we're also zooming in, and we're not talking about voltage regulators. We're talking about digital design. And even in digital design, we are not talking about memories. We are talking about logic design. So we go so deep, so what's the point? But really, logic design is one of the biggest pain points of the industry and how to verify it well. And if we look at, there are two types of logic design, asynchronous design, which is not used a lot, and I'll introduce it very finely. And then synchronous design, which is the majority of logic design being carried out in industry. So logic design is basically making a pizza. Say we have a pineapple and olives pizza. And we need to lay out the dough, which takes us 3 minutes, spread the cheese, takes us 2 minutes, add the olives, 1 minute, add the pineapple, 1 minute, and heat in the oven for 5 minutes. So in total, the throughput that we are able to carry out from this sequential system is 1 pizza every 12 minutes, and the latency for this system is 12 minutes until that pizza is ready. So basically, the same metric from throughput and latency. So hardware is actually making a pizza factory, making an assembly line. So if we take those operations and we chain them, and we say each part of this chain can work concurrently, then we're actually doing an assembly line. So in this case, we made an assembly line, and now we need to know how to divide the work between the stations. And if we are going with the asynchronous solution, so each station consumes and produces the partially made pizza as quick as it can, then the throughput is 1 pizza every 5 minutes, because that's the bottleneck of the longest part of the chain. But it still takes us 12 minutes until that pizza is ready. But asynchronous design is very complex to implement and maintain, so let's skip over that. The bad synchronous solution is saying, okay, we have a clock, like a global clock, that all these stations are working at, and each step of the clock, we move the half-made pizza from one step to the other. But this is very bad, because indeed we get a throughput of one pizza every 5 minutes, but now the latency is 25 minutes from when we begin until we get that pizza. Additionally, we have significant inefficiency, because the adding a pineapple station is not optimized. It's basically that guy is resting. We pay him 80% salary that he doesn't own. So if we look at the potential of how to optimize hardware design, or pizza design, in this case, we combine the station to make an optimized pipeline. In this case, when I divided to have the oven and the pineapple together, and the rest of these stations together, I get a 6 minutes for each stage of this pipeline. So one pizza every 6 minutes. And the latency is 12 minutes until that pizza is ready. So we reached a system that is pretty easy to implement, and it's pretty optimal, because we still get a very good throughput, and the latency was not interrupted. This is how to design. This is basically how to design. But if you think of how to design, the recipe for pizza has not changed. Okay? It's the same recipe for pizza, but you get different optimization according to what you implemented. So my goal when doing how to design is how I can describe the hardware design in a way that the compiler can infer such things automatically. So how to design is really like making a pizza, but you need to implement, instead of a pizza, you need to implement very complex arithmetic logic functions. They need to be very time-critical, nanosecond resolutions. They need to be highly reliable, secured, efficient, and have very good throughput. And the real challenge of it all is we're talking about synchronous and digital design, but it's fake, because nothing is truly synchronous and nothing is truly digital. Everything is analog, everything is asynchronous. So where hardware designers usually fall, that everything works in simulation, but they try to make the chip or make the FPGA and nothing works, is because they miscalculate that last step of what the real challenge is all about. So I talked about how to design. When we do logic design, we target two typical devices. One is called FPGA, Field Programmable Gate Array, and one is called ASIC, Application-Specific Integrated Circuit. And FPGA is, from its name, it's programmable, not pizza. And because it's programmable, it enables us to change the interconnected circuitry within that FPGA. An ASIC is actually, FPGA is a type of ASIC. An ASIC is something that you create once and you cannot change it. Each has their own benefits. Aside from programmability, ASIC is, of course, if you have big quantities, that's your best cost per component. But there are other things that you need to care about when you target each of them. So to target them, we are using hardware description languages. So why do we need hardware description languages? Wiseman once said, great many logic gates require great programmability. Then it died out of pizzas. And if we look at the core hardware design modeling, there are three things that we need to care about. One is actually two things, time and state, and they have interconnected relationship, but they are not the same. Hardware designers always confuse them, but they are not the same. We have concurrency, which should be concurrent first and not as a side product. And we need to care about data validity. All these things, the classic von Neumann type of C language doesn't work. It doesn't fit this model. So, but what about the standard languages? So Verilog and VHDL are used throughout the industry, but Verilog is lacking type safety. VHDL is very type safe, but too verbose. And both have an event-driven abstraction, which is highly confusing to beginners, and it's very challenging for the design aspects. And you think, again, about Scala tooling problem. These languages exist and their spec exists for so long time, and the tools still don't agree of what those languages should be. So you run it with one tool, you run it with a different tool, you get different results. So that's very unexpected, and which is a very big pain point. So there are alternatives. We are not the first trying to create our own language. How to design is basically every week we have a channel we call reset the counter. There's new language doing how to design, new host language. And I divide them into languages which are like DFiant HDL, DSL in a different language. And there are languages with different syntaxes. But I'll be talking about DFiant HDL. So how to design with DFiant HDL, I think, is pretty simple. But DFiant HDL actually introduces 3 levels of abstraction within the same language. The first, the lowest abstraction is equivalent to visual Verilog, the event-driven one. The register transfer abstraction is equivalent to, if you heard of Chisel, that's a similar abstraction. And the top one, the data flow one, enables us to describe the what instead of the how, to focus on the function instead of the implementation. And the 3 abstractions are designed to work and mix and match together. So let's do our first how we design. So I'll import the library, and I create a class, demo extends RT-design. I created a register transfer level design. That's it, we're fine, we're golden, I go. But this is just an empty shell at the moment. I also add a top annotation. What that top annotation is doing is actually using a Scala compiler plugin. It's creating a runnable program. So you can immediately just run Scala run top_demo, and it will enable you to build, to compile, to lint that program using external tools. Now let's add some stuff. I'm adding a LED's output and a direction input. So the LED's is 8 bits, and its output is also a register, initialized to 0000001. And I add the input there. So construction is an effect within the system, but it's limited within the context of the design. So everything that you describe has an effect that causes a construction element. So now I added another register, which is a counter, and it counts until 5 million cycles, which is targeting that board over there. And now I populate it a little bit more, and then we get something a little bit more complex, but basically, it gives us this circuit. So I talked about the register. What is a register? So a sequence circuit has a clock, and it has a component called a register. A register only always saves a value, and it only changes the output of its value, its output when the clock ticks, in this case, in the rising edge tick, then the input of the register gets transferred to the output of the register. Until the next clock tick, the register reserves its value. So in this case, if we look at the counter, it needs to choose right here between right rotation and left rotation. And the laser pointer not seem, let me point with the mouse. So here we have everything, all the registers I refer, when I assign to them, I assign to their D-in, data in. So when I refer to a register, I always refer to the output by default. And when I want to write to a register, I write to their entrance, but it's not actually writing, it's not mutation, it's a copy and set. It's changing the reference for what is inside. So by applying beforehand, there was a loop here, and afterhand, we got that loop connected to something else. So the connection is changing, but not the mutation.
I'm a bit confused by the symbolic operator.
So the symbolic, these operators? So these operators means construction. So I have a type and the direction and the modifier. So I construct LED's output and a bit input. They also can mean connection in DFiant HDL. So let's see a live demo. So here we have the board that we want to program. And here we have the same code that I've shown you before, but it also has something else. It has resource connections. And the resource connections, it's what enables that top design connected to its external world. So I have here this, this board that we have here is actually illustrated in this ASCII design over here. So I'm connected with, in PMOD J4, it's a standard connector for the board, and PMOD J6 with different boards. Both of them have 8 LEDs. And actually they are from different vendors, so they are have different ordering internally, but I made them so that they are easy to connect to. So basically what we have here is a connection is that we have this board over here, the PMOD board is connected to J4, and this PMOD connected to J4, and this PMOD is connected to J6. So by creating this connection between the board that I instantiated and the connector, everything else that you need to take care of is taken care of for yourself. So if I run, and I run just elaborate, sorry. I'm sorry?
Like an extra dash dash to pass the arguments.
I don't know what happened here.
Then you need an extra dash dash before elaborate.
Oh, yeah. Sorry, Scala CLI. I forget sometimes. So now it elaborated and it printed my elaboration. So I see my design that I created before, but it has a lot of annotations that I could have written manually, but everything was connected. So the device that I'm using, the vendor that I'm using, the clock that I'm using, the clock is 50 megahertz, and everything was carried out automatically. So all of this is now, when I want to run the program, is carried out to the tool automatically. So now what I'm doing is running an external builder, and then it's after it finished building its programming. And when we look at the board, we see this small LED walking thing. What I've done here in a couple of minutes, indeed writing it takes a little bit of time, but for a beginner to write it and do it successfully is very, very big, very, very difficult. Because all these LED, how they connect to that FPGA is very cumbersome, how you connect them. And it's also not only the routing to the FPGA, the polarity. These board's LEDs and these board's LEDs don't have the same polarity. So one is active high and one active low. One I need to push one logic to turn on, the other I need to push 0 logic to turn on. But here, all I need to do to change this, I change from the PMOD LED from J6 to from J4 to J6, and I change the PMOD board type because it's a different board to this PMOD board. That's it. That's all I've done so far. And now I will rerun the build and programming step. Sorry, and of course something is not working. 8. Oh, yes, sorry. I forgot to change. Yeah, I'm not sure, so let's, sorry, let's continue with the demo. So in this case, when the laws are changing, they are changing according to the frequency of the clock. Now, all of these things that I defined in this code that are sensitive to the clock, theoretically in the data flow domain, you don't need to mention anything. You just require to define a timer, and it derives everything automatically. So the magic of Scala 3 is really what enables us to do a lot of things here. And let's see some things that are applicable everywhere. For example, compile time plus runtime checking. Let's say I have a function here, positive, that I want to check its argument that it's really positive. But I want, if the parameter is null at compile time, I want to show a compile time check error. If the parameter is not null at compile time, I want to do a runtime check error. So I want to have both. Internally in DFHDL, I have this checked function, which enables you to define, using type lambdas, you can define what is the condition and what is the error. So you can compose the errors using the singleton ops of Scala and the type lambdas, and you can have this positive that defines the condition t bigger than 0, and then composes the full string. And that string appears as an error message in compile time, and if the compile time is not null, as an exception with that same error message at runtime. So this is one thing that you can do only in Scala 3. Also, a neat concept that Scala enables us to do with very simple syntax is what I call by-type parameter application. Say we have an option, many options that we want to define for a function. So we can go about it by applying them by order or by name. But if we apply that, we make it so that every option has unique syntax, a unique type. That takes us a little bit of more cumbersome work in the library sense. So the library that defines the option uses all these opaque types and defines the different sub-options. But at the user level, all the user needs to do is, just write given with the full type and then assign a value. And everything is propagated automatically. Now, for just small options, it seems kind of redundant, but if we look at DFiant HDL, we have at the top annotation hidden a lot of implicit functions, many options with sub-options inside of them. But the user doesn't need to care about any of those things. So they only apply the options that they require to do so. By the way, I have not shown this. So it also acts with the button to change the direction. So sorry, I forgot. So, yeah. So this kind of concept, maybe it's possible with future macro annotations to make it simpler, I don't know. But I very like this concept of introducing options. Also, compiler plugin magic. If you've seen from the code, we are using Scala if, and we can also have Scala match, and we can use for and while within the data flow, within the DFiant HDL construction code. This enables us to construct hardware very easily, and we don't need special operations to do that like other languages do. Sorry, how much time we have?
15 minutes.
What?
15 minutes.
15 minutes? Okay. And we also have meta information generation. So the name, the source positioning, and the annotations, everything is passed to the hardware design. Also, the onCreate. So Scala 3 deprecated on delayed init, and you need that to know when design is finished constructing. So the onCreate option is also done with compiler plugin. And also to have context propagation throughout classes without being implicit, using implicit all the way. So that also helps the compiler plugin. And we have top application generation, as you have seen so far. And another thing that I like is context-sensitive overloading, what I call it. In DFHDL, we want to use assert like we're using in assert has a meaning in how to design simulation, so assert is important to write. But I don't want assert to make Scala assertion. I want it to be used in the context of DFHDL to make a hardware assertion. But how do I differentiate the default Scala assertion without creating a new different named assert method? So that's what context-sensitive overloading is all about. So in DFHDL, we can know what type of scope we have during using implicit. So we have a global scope by default, but there's local scope that's been introduced, design scope, domain scope, and process scope. And within our assert method, we actually override the default assert method and refer to it when we need. So using compile time sum and from, we can look at if we have a local scope, then we refer to the assert defined HDL assert. So the user doesn't know. The user writes assert. They use their mental model that they're writing how to design and just use assert. They don't need to worry about what type of assert that they're doing. But when they're using assert outside of a how to design, they want their good old assert back. So they have ability to use inline assert to do just that. So let's see if you've been paying attention. You have the option of attending, participating in this quiz. Go to slido.com and enter this code. 3 simple questions, and you can go on and be an FPGA developer of your own. So I'll give you a minute to try it out, to enter, and then we can move on. Code is 2986226. Okay? First question. What is the real acronym meaning of FPGA? Don't look at what others are doing. So the right answer is free programmable gate array, indeed. What is the demo board oscillator frequency? I mentioned it very, very briefly. Okay, 50 megahertz. And then, which of the following 3 Scala 3 features was not used in implementing Defiant HDL? Indeed. Let's see who won. Jacob? So come to me after the talk, and I can give you your glowing lead. So now we have time, a little bit of time for questions.
Question about the hardware. Do you support other hardware than this particular board?
Yeah. Currently, the board by Digilant. But if you look at how things are implemented, it's fairly easy to add one yourself. For example, if we go into the tank primer, we can see that it's actually a composition of the core board and the base board. And how it's composed, just basically a connector between the boards. So, and the tank core is composed of the FPGA device, and then an oscillator, and then it has power things to map the power networks, and then has the B2B connector and the connections. So everything is just connected. So you see J1, P16, connected to FPGA, IOs by name, and the name of the IO. So theoretically, even an AI can do it if you give it a netlist, like I did. So, so all of these connections are things that you as a user needs to follow when you design it for the first time, when you use how to design this design. But once someone made that board, you don't need to handle all of these connections. So all of the constraints can come from different things. For example, if you connect to a button, a different constraint comes from using that button. I didn't go on about it much, but what we have here, I'll close this. I have this given expected active state for LEDs and buttons. Why? Because again, you as the user of the library, as a designer of this LED thing, thought that lighting a LED is active high. So you're saying, okay, LED is on, that's when the LED is active. And when the button is pressed, that is when the button is active. But the person that made that board made it differently. But you don't care. The type system works it out for you. So because you have different types connected, one is inverted, one is not, then it's already applying the board automatically for you. So when you map these kind of boards, you can do that yourself. You use the type system, and the type system handles everything for you.
But there's also the programming of the board itself, the internal logic of the FPGA. And that's
so everything I'm running external tools. So currently I'm using the SciPy Go-In tool, and I'm using Vivado for the Xilinx tool, and by next month I will have a demo that 4 boards for four different vendors, everything working with the same program.
Thank you.
Hi, maybe a question about scalability, like how does it scale with all those bits added in the compiler? Did you try like
Can you speak a little bit louder?
Yeah, sorry, about scalability of your tool, since you added a lot of things in the compiler, like a custom compiler plugin, like did you try with like thousands of lines of code or tens of thousands of, like did you run some benchmark on the size?
Okay, you asked about the scalability of a design if I attempted a very, very large design for the compiler plugin. So the compiler plugin, no. So I didn't write a very big Scala program. I did write an AES encryption, which is kind of big, and then after it elaborated, printed it and placed it back. Actually, the thing that was the most difficult about it is because when you have a very large population of code within a class, you are limited by the JVM. So that's the only limiting factor, basically. But that's when you describe hardware yourself, you don't flatten your design like that. So I've seen no scalability issues yet. That it's compiling very, very fast. At the moment, again, medium designs, not something large like Chisel people are doing, for example.
So you said you're not using capture checking yet, but have you already thought of use cases for it?
Yeah. So what I really want currently, I think you also know of this problem as well, is that first of all, by the way, regarding capabilities, there is somewhat a thing like a capability tracking. For example, the din factor here is, if I didn't have the din, I would get a compiler error. And because I have the din can come also after the selection. For example, here I can assign to parts of part of the LEDs. So the capability of mutation, the capability of assignment is going through different types. So when one type is derived from another, there is such a thing of a capability, but it could have been much easier to write it maybe as a true capability. That's one thing. But
what are you tracking at compile time, like multiple assignments?
So at compile time, I'm tracking the assignability, basically. But also in this case, the register assignability, so that you can actually, this is truly a register in this case. But what I most want out of the capabilities, and currently I don't know if it will be, capture checking, I don't know if it will be possible, is when we have different designs instantiated in one in another, I want to know if a design is truly pure, that it's using only parameters that it gets not from anywhere else. And once I do that, then I know that I don't need to reinstantiate that design again and again. I can, instead of at compile time, remove that design every instantiation inside except from the first, and reuse old cached instantiations. So I can save a lot of runtime during elaboration. But again, I don't know if it will be possible using the separation checking.
Thanks, Jonas here. I'm curious about the target audience. Is it hobbyists or actually engineering departments that would onboard on the Scala?
So
Scala DSL like that?
basically, I want to bring in 100,000 Hardware developers into Scala. I think Scala has great potential in hardware design because, again, hardware is immutable. That's basically it. So functional languages work great for hardware. But to do it right, it's challenging. There are various aspects to it. But just to get a working demo like this, and to have this demo now working when you connect a different board without changing anything else besides the resource connection, that's something that rarely exists. There is some things that are made with Python, like this library called Litex for that. But I can also accommodate for different clock frequencies and things like that. So it can be very challenging for a beginner. But once we solve that problem, we also solve problems for industry, for that lack of knowledge in the industry, and also the increasing productivity gaps. When you want to design, you don't want to care about things that are irrelevant that the compiler can do for you. So when you use higher abstraction for those specific cases, you only get a win for that.
I think that's all the questions. Thanks, Yoga.
Thank you.